12,000 years ago, in the span of less than a decade, Europe was plunged into a deep freeze, so sudden and so violent that entire ecosystems collapsed before they had time to adapt. Forests that had taken thousands of years to grow died within a single human lifetime. Ice sheets that had been retreating for millennia suddenly reversed course and came roaring back. And the trigger for this catastrophe was not a meteor. It was not a volcano. It was something far quieter, far more patient, and far more dangerous. It was the ocean itself, changing its mind about which direction to flow. Now, in the spring of 2026, scientists have found the clearest evidence yet that the same system responsible for that ancient catastrophe is weakening again. And this time, we are the ones living inside the experiment. This is the story of the Atlantic Meridional Overturning Circulation, a phrase so clinical, so bureaucratic, that it almost hides the staggering truth of what it actually describes. Because underneath that dry, scientific name lies one of the most powerful engines on planet Earth, a vast invisible conveyor belt of water stretching from the icy edges of Greenland to the tropical currents of the equator, quietly regulating the climate of an entire hemisphere for thousands of years without a single human being noticing it was there, till now. Picture it. Warm water, dense with salt, drifts north along the surface of the Atlantic Ocean, carrying heat absorbed near the equator all the way up toward the coasts of Iceland, Greenland, and northern Europe. As it travels, it releases that heat into the atmosphere, which is the very reason why cities like London and Paris enjoy mild winters despite sitting at the same frozen latitude as parts of Canada that are buried in snow for half the year. Then, having given up its warmth, the water grows colder and denser still. And in a handful of specific locations in the far North Atlantic, it does something remarkable. It sinks, thousands of feet down, plunging into the deep ocean where it begins a long, silent journey south again, completing a loop that has operated like clockwork for longer than human civilization has existed. This single, continuous motion moves an almost incomprehensible volume of water. Scientists measure its strength in a unit called a sverdrup, each one equal to 1 million cubic meters of seawater flowing past a single point every second. At its healthiest, the AMOC moves roughly 20 sverdrups of water through this loop continuously, day and night, season after season, an engine so vast it makes every river on Earth combined look like a trickle from a garden hose. But an engine, no matter how vast, can slow down. And for years, scientists have warned that human-driven climate change could be doing exactly that. Here is the mechanism, and it is almost unbearably elegant in its cruelty. The entire system depends on cold, salty water becoming dense enough to sink. But climate change is disrupting both halves of that equation at once. Rising global temperatures are warming the surface waters of the North Atlantic, making them lighter and less likely to sink. And at the same time, the accelerating melt of Greenland's ice sheet is pouring enormous volumes of fresh, non-salty water directly into the very region where the sinking is supposed to happen. Fresh water is less dense than salty water. Pour enough of it into the engine room of this system, and the sinking slows. The pump begins to falter. For decades, this was mostly a story told through climate models, computer simulations, projecting what might happen over the coming century if warming continued unchecked. Real-world, continuous observational data only began in 2004, when an international network of scientific instruments called the Rapid Array was installed across the Atlantic at 26 degrees north latitude, finally giving researchers a direct physical window into the strength of the current in real time. And in April of 2026, researchers led by physical oceanographer Shane Ellipet at the University of Miami's Rosenstiel School of Marine Atmospheric and Earth Science published findings that sent a shockwave through the climate science community. Using data collected across 4 separate monitoring locations along the western, the boundary of the Atlantic spanning roughly 2 decades, they found consistent, measurable weakening at every single site. Every single one, Ellipet described this consistency as deeply significant, comparing the western boundary of the Atlantic to a canary in a coal mine for the entire circulation system. This was not an anomaly at one measuring station that could be explained away by local weather or short-term variability. This was a pattern repeating across an enormous stretch of ocean. and it aligned precisely with what climate models had been predicting for years. Independent researchers, including marine and atmospheric scientist René van Westen at Utrecht University, described the findings as some of the strongest direct observational evidence yet that the present-day AMOC is genuinely, measurably declining. But the story does not end with a slow, gentle weakening. This is where the science becomes genuinely unsettling, because the AMOC is not necessarily a system that fades away gradually, predictably, like a fire slowly running out of fuel. Growing evidence suggests it may instead behave like a switch, a system capable of existing in two distinct stable states, one strong and circulating, one weak and nearly collapsed, with a violent, rapid transition between them once a critical threshold is crossed. Scientists call this a tipping point, and once a system tips, there may be no walking it back. The last time this circulation collapsed, roughly 12,000 years ago, it triggered a sudden climatic event known to paleoclimatologists as the Younger Dryas, a near-instantaneous return to Ice Age conditions across the North Atlantic region that lasted for well over 1,000 years. Researchers studying ancient sediment cores, ice layers, and long-buried climate records have reconstructed the AMOC's behavior stretching back over 1,000 years. And the story they tell is troubling. For most of that long history, the circulation remained relatively stable. But the reconstructions show a marked and unusual decline beginning in the modern industrial era, coinciding precisely with the timeline of human-driven greenhouse gas emissions, exactly the kind of anthropogenic signature scientists feared they might eventually find. Not every scientist agrees on how fast this collapse could unfold, or whether a full collapse is even likely within this century. The scientific debate is real, and it is fierce. Some researchers, using different modeling approaches that better account for small-scale ocean turbulence, argue the weakening projected for this century may be more limited than the most alarming scenarios suggest. Perhaps 18 to 43% by the year 2100, rather than a complete shutdown? Other studies, incorporating the accelerating pace of Greenland's ice melt into their models, warn that a full collapse could arrive far sooner than anyone previously believed, potentially within the coming decades rather than the coming centuries. This uncertainty is not a weakness in the science. It is the very reason scientists are racing to gather more data, refine their models, and understand exactly where the true tipping point lies before humanity crosses it without knowing. And the consequences of getting this wrong are almost too large to comprehend. If the AMOC were to collapse, or even weaken dramatically beyond what we are already witnessing, the effects would ripple across the entire planet, not gently, but violently and unevenly. Northern Europe, paradoxically, could plunge into far colder winters, robbed of the ocean heat that currently keeps its climate mild despite its far northern latitude. Sea levels along the eastern coast of the United States could rise even faster than the already alarming pace. Driven by melting ice sheets, because a weakened AMOC changes the way water piles up, against coastlines, monsoon systems that hundreds of millions of people across Africa, India, South America depend on for their annual harvests could shift unpredictably, throwing agricultural cycles that have remained stable for thousands of years into sudden chaos. And weather patterns across the entire northern hemisphere, from the intensity of hurricanes to the frequency of extreme storms, could be reshaped in ways scientists are still struggling to fully model. This is not a distant abstract threat confined to computer projections and academic papers. Scientists are already documenting its early fingerprints on the world we live in right now. Researchers studying the Southern Ocean near Antarctica have identified warm water creeping steadily closer to the fragile ice shelves that hold back much of the continent's ice. Slow, quiet infiltration that could accelerate global sea level rise if those shelves give way. In the Arctic, scientists say the rapid disappearance of sea ice may have already pushed the region across its own dangerous threshold, triggering a hidden chemical shift that is stripping vital nutrients from the water, the very foundation that supports the plankton at the base of the entire Arctic food chain. And across the globe, ocean surface temperatures have been breaking records with alarming regularity. With the European Union's Copernicus Marine blanketing more than 80% of the entire global ocean simultaneously, the ocean, in other words, is not simply warming quietly in the background of our lives. It is beginning to behave differently in measurable, interconnected ways across nearly every basin on the planet all at once. And here's the part of the story that should genuinely humble us. We very nearly lost the ability to see any of this happening. The scientific instruments capable of detecting these shifts, the moored buoys, the drifting floats, the research vessels, the underwater gliders that make up what oceanographers call the Global Ocean Observing System, form a fragile, expensive, and chronically underfunded global network. It is this quiet infrastructure, largely invisible to the public, that gave scientists the data to identify the AMOC's weakening in the first place. The same infrastructure researchers now warn is increasingly at risk from funding cuts and political neglect at the precise moment humanity needs it most. Consider the strange irony embedded in that fact. Humanity built the tools capable of detecting a threat that could reshape civilization as we know it. And having built those tools, we are now debating whether we can afford to keep them running. But amid the uncertainty, amid the fierce scientific debate, amid the sobering data pouring in from every corner of the world's oceans, there remains something genuinely remarkable happening here. For the first time in human history, we are not simply the victims of a changing planet, discovering catastrophe only after it has already arrived. The way our ancestors experienced the sudden freeze of the Younger Dryas 12, 1,000 years ago with no understanding of why the world around them was collapsing. We can see it coming. We have satellites in orbit, arrays of instruments stretched across ocean basins, ice cores drilled from the heart of ancient glaciers, and some of the most the human mind, all working in concert to give us something no civilization before us has ever possessed: advance warning. The question that remains, the one no scientific paper can fully answer, is whether we will use that warning in time. Because right now, deep beneath the surface of the North Atlantic, in the cold, dark waters off the coast of Greenland, an ancient engine that has regulated the climate of an entire hemisphere for thousands of years is quietly, measurably faltering. It does not announce itself with headlines or sirens. It reveals itself. Only through the patient, careful work of scientists lowering instruments into freezing water, compiling decades of data point by data point, or watching a pattern emerge with growing, undeniable clarity. The last time this system shifted, it happened before agriculture existed, before cities existed, before writing existed, and it took 1,000 years for the world to recover. This time, we will not have the excuse of not knowing. We are watching it happen in real time with our own instruments in our own lifetimes. And what humanity chooses to do with that knowledge in the years immediately ahead of us may determine whether the story of the Atlantic's great conveyor belt becomes a warning we heeded, or a catastrophe we watched arrive in slow motion, 1 degree, one spurred up, one melting glacier at a time.